Unit 2. The role of language in teaching chemistry. Unit Introduction. Language is an important tool for communication. It is used for expression of ideas and feelings of individuals. Language is central to learning. It is what we use to convey meanings of concepts, expression of ideas, and representation of phenomena. In chemistry, we use symbols, formulas, equations, and words to teach our students different chemical concepts. Language is context development, and the meanings attached to language are derived from experience. Teaching chemical language is like teaching a new language. Symbolic representations used in chemistry may be unfamiliar to students. When the events represented are also unfamiliar, problem occurs in understanding the concept. Teachers must help their students overcome such problems, connecting the symbolic language of chemistry with the macroscopic world of experience. This unit contains some language problems in teaching chemical language and methods of teaching some common and basic chemical languages used to teach chemistry. Unit Learning Outcomes. On successful completion of this unit, you will be able to manage language-related problems in teaching learning chemistry. Identify problems related to language in teaching learning chemistry and suggest possible solutions to the problems. Integrate language and mathematical skills in teaching learning chemistry. Employ scheme which is important to solve language problems. Manage the active participation of students in overcoming the problem of translating chemical languages. 2.1. General language development. In-text question. Language enables individuals to engage socially, initially within the family, and later in an ever-widening network of relationships and cultural experiences. It enables individuals to give expression to their feelings, ideas, and concerns. It is through language that they communicate their personal needs and claim their rightful place in society. Language is central to learning. It is the primary tool through which teachers mediate and through which students learn across the whole curriculum. Much of what the students learns and the way he/she learns comes from the interaction of language and experience. Through naming, describing, classifying, and modifying things and ideas, knowledge is extended, and the command of language developed. In learning language, reading skills are developed by deciphering symbols, in which different shapes are recognized as letters that can be distinguished from each other. Words that denote ideas are used to represent different characteristics and actions which give sense. In reading, the external environment is the printed symbols that we use to interpret. It is a bottom-up processing where the symbols and other external stimuli evolve knowledge, where the process of interpreting sensory information comes from the external world. The top-down processing refers to the way existing schemes compete with one another to provide the best account for the world's use. Here on C. Brown Collins and Harris, 1978, p. 12. It is governed by existing knowledge and by contextual cues that lead us to relate particular segments of knowledge to the message under consideration. Reading skills development of students is the result of effort made by the faculty as a whole rather than by each teacher acting independently. But as a chemistry teacher, you should help students in developing best reading skills which help them understand the subject. Chemistry students should be good readers that can process English automatically when they read their chemistry textbooks. They decode well, and they have large vocabularies. When new ideas are introduced, students encounter many unfamiliar words or familiar ones in unfamiliar context. They can't do much of the work needed to learn the history, the unfamiliar words or familiar words with unfamiliar context. The efforts of students to develop their skill must be supported by teachers making use of their superior knowledge and experience. Teachers can easily tell students meaning of words, but always telling them the meaning of a word increases the information without improving the intellectual skills that allow them to derive meaning of their own. Reading is a thinking process, and that readers must learn to be good thinkers. Readers must learn to use contextual cues, syntactic cues, semantic cues, and word attack skills to derive meaning. Such skills do not develop automatically, but teachers should encourage their development in the process of teaching. equals when they ask their students questions, and when they respond to students who ask for help with words. The following are some suggestions for developing these skills to offer. 1975. 1. Ask the students what they think the word means. Students often make good hypotheses about word meaning but need confirmation. If we are able to confirm their hypothesis, we reinforce their faith in the process they are using. If their analyses have led to incorrect hypothesis, we can often show them where their thinking went astray, thus providing corrective feedback concerning the logical process they are using. 2. If students have not done so, ask them to read to the end of the sentence or the end of the paragraph to see if any contextual cues can help. If the word is in some chemical context, such as the description of some chemical change, ask the students to describe the process to see if that description provides useful cues. This practice not only encourages students to relate language to the chemical events that are described, it also provides you with useful information about how well the student understands those events. 3. If the word is derived from some root chemical or other, ask students if they recognize the root and know its meaning. Then see if they can guess the meaning of the derived word. 4. Encourage the students to use dictionary. 5. You need not wait for students to ask the meaning of a word. When you use a new word or one has been in a reading assignment, initiate the process described above by asking students what they think the word means. If this questioning is done in a group setting, discussion among students can reveal the tools that students are using to derive meaning and can provide excellent opportunities for them to practice rational thought. Students need to develop oral language for sharing the ideas they have learned, asking good questions, and seeking and sharing information. Oral language play a critical role in students' overall academic progress. Within the area of oral language, spontaneous language expression and scuffled oral expression are important. Spontaneous language lessons use concepts from the content area to help students gain the main idea and the interrelations among major concepts. On the other hand, scuffled oral expression lessons provide students the time to practice the use of the words and to work on the expressing their ideas properly. An important aspect of oral language development lesson is instruction in the technical aspects of language use. Such instruction focuses on vocabulary development, opportunities to hear and to use basic sentence structures and gain practice in using appropriate instruction styles. Communicative competence, being able to get your message across, is the driving force behind oral language development, and both types of lessons, spontaneous and scuffled, are necessary as a regular part of instruction. Another useful idea for language development is organizing and integrating language and content teaching which are direct towards content-obligatory or content-compatible language. Snow, Met, and Genesi, 1989. Content-obligatory language includes the vocabulary and language structures that are key to understanding and expressing ideas relates to content. For example, in order to discuss about compounds, students need to know the name of the compound and type and number of different atoms that form the compound, and how they are combined. Content-compatible language includes the vocabulary and structures that complement these ideas and can be utilized for additional practice on the content in focus. In the above example, the idea of a compound can be extended to representation of the compound using molecular formula which uses symbols of elements in the compound. Calculations of molecular mass using atomic masses of elements are another extension of activities for describing the compound. Language is what we use to convey meaning of concepts. In concept learning, meaning is context-dependent, and is what we attach to the language, written or spoken, which results from top-down processing under the control of existing schemes and sounds. Spoken language and ordinary writing allows readers and listeners to infer meanings. The development of reading skills and oral language is the result of the effort made by teachers as well as students in the process of learning. You are expected to make sure that students develop their reading skills and oral language when teaching different concepts by encouraging them to read subject contents and express their views. Activity 2.1. 2.2. Language problems in teaching chemistry. Activity 2.2. Chemistry is basically a science of the composition, structure, properties, and reactions of the substances. Chemistry is an experimental science that shows transformation of substances to different forms. When teaching chemistry, we use language, formal and chemical language, to communicate knowledge to our students. Chemical language is used to express meaning of concepts. It is essential to understand how chemical language is used, what rules govern its use, and what consequences the use of the language has for teaching chemistry. Chemical language should express the composition, structure, properties, and reactions of substances. The language of chemistry consists of the set of symbols to represent elements, formulas to represent compounds using elements, rules for combination of atoms to form compounds, rules for reaction equations, names to identify compounds, etc. There are many problems related to the use of language for teaching chemistry. Teachers face different problems when they are teaching chemical concepts at different levels. Some of language-related difficulties of chemistry students are a lack of understanding of familiar words to convey meaning in chemistry. Example: the use of words such as reaction, product, solution, etc. to express chemical concepts against their common meanings. B. Lack of understanding of technical terms introduced in the study of chemistry. Example: the use of technical terms such as mole, molarity, normality, formality, oxidation, reduction, etc. to represent different quantities and phenomena. C. Describing or attributing a familiar meaning to a common word used in a technical sense. Example: the use of the common word solution, which have a usual meaning of solving a problem or a correct answer to a problem, to represent a liquid mixture of a solute minor component distributed uniformly in a solvent major component. D. Using everyday meaning to drawing correct conclusions about chemical events. Example: The common understanding burning and chemical combination of substances with oxygen, or the common understanding of salt table salt with compounds forms by the reaction between acids and bases. In text question, the contextual understanding of the meaning of words is one major problem of teaching chemical language. The different point that you should consider in teaching meanings of terms used to represent concepts, problems of word meanings can be avoided by making your students know different cues to word meaning. Linguistic cues are used to differentiate the meaning of a word in different contexts. For example, the use of the word agent gives different meaning in the follows two sentences. Mrs. Smith applied to the firm to become an agent to sell cosmetics. An agent changes something which brings about the change. Science cues are also important for understanding meaning of a word. The knowledge that words that are understood in isolation will not be seen to apply in a science context, unless the science context is also understood. Look at the meaning of the word detect used in the following two sentences. If I detect something, I find it out. The use of a flame allows hydrogen gas to be detected. The first statement is clear for students to understand clearly the meaning of detect from their common experience, that when detect some object they are identifying the object. In the second statement, students cannot associate with the fact that it is a way of detecting hydrogen, unless they have seen lighted splint stuck into a bottle of hydrogen gas or oxygen gas, as a test for hydrogen or oxygen gas. These examples make clear the idea that problem of reading words in the context in which it is used to understand its meaning is one problem that a chemistry teacher should address by teaching students what inferences are appropriate for the word used in that particular content in teaching specific concepts. The preceding examples illustrate problems of using an ordinary word in a scientist's context without changing the meaning of the word. Additional problems occur when the ordinary word takes on a new meaning, that is, when ordinary words are given technical meaning to express specific conditions. The following question item illustrates this point. As used in everyday speech, strong means concentrated, as in strong coffee, or powerful, as in strong detergent, but in chemistry it means highly dissociated, as in strong detergent. Here, students' understanding of a word from the real-world experience hinders rather than helps in the understanding of the word in a new and unusual sense. Even when the new meaning has been learned, the more familiar and well-practiced meaning may win out as top-down processing impose meaning in the chemistry context. In everyday speech, the greater familiarity with the content of communications and the large number of contextual cues from which to infer meaning allows students to get along without totally understanding familiar words. But when the same words are used in chemistry, lay redundancy, more unfamiliarity, and new meanings for the world exist. In addition, tasks that we expect students to perform in science require a precision in meaning that goes beyond what is required in other settings. In particular, any message conveyed in a context that provides redundancy, i.e., where meaning can be obtained from words, facial expressions, intonation, pictures, or other sources, a person may perform very well without a precise understanding of the words. In a context that is devoid of redundancy, precision in word meaning is important. As a result, the students may fail to comprehend without realizing why. Activity 2.3. The other problem to comprehension is the use of different terms by students without knowing what they mean, and without knowing that they do not know. Students commonly are area, volume, pressure, density, and similar terms to solve a problem, but students sometimes use these terms without knowing what they mean. For example, students multiply the length and width of a sheet of paper to find its area, but they cannot say what the resulting product is telling them about the paper. Similarly, when asked how to find the size of a surface such as tabletop, or what unites would be used to describe the size of the surface, or what they are telling about the table distance, arc, volume, mass, etc., these students cannot respond. When told that the room they are standing in has a volume of 30m3, and asked what that says about the room, the students respond that it tells them how much there is on all the walls, and the floor, and the ceiling. When students who have correctly calculated the density of several objects are handed two objects of the same size, but different masses, and are asked which has the greater density, masses, and are asked which has the greater density, they are often unable to say. Osborne and Sosgrove, 1983. The distinct occurrence of such problems makes them difficult to detect and remediate, but the problem is real and needs attention. This is what you, as a teacher, should realize, that different students interpret the same text differently, and design different methods that help you to reveal not only whether or not a student understood, but what that student has understood. The need to teach technical terms is obvious. Most textbooks include lists, definitions, and other assets for teaching such terms. The awareness of how the relationships involving a word, the ways a word may and may not be used, and the changes in word meaning when words are used in various contexts is very important. The meaning of words evolves over time. This is also true for technical terms. However, technical terms are frequently taught as though they have a fixed, commonly accepted meaning. When a word concept is introduced, students are frequently taught the definition of the word concept. When the word is later used in a new and different context, the changed meaning of the word is frequently ignored, and students are left to sort out the meaning for themselves with few contextual cues to aid them. This is a problem which is encountered due to attention not given to conditions in which one word can have many meanings depending on the context under which it is used. Assignment 2.1. 2.3. Teaching chemical language. Chemistry is a science of the composition, structure, properties, and reactions of substances. It has its own language, which consists of rules and regulations, conventions, to help organize the representation of substances and show the changes that they undergo at atomic level. The language of chemistry consists of elements, chemical symbols, chemical formulas, chemical equations, and chemical names. Chemical language also includes rules for combination of elements in formulas, rules for reaction equations, laws, models, and theories that govern the behavior of elements and compounds. It provides a vocabulary to name and talk about substances. Teachers should know how to teach chemical language that is necessary for understanding of different chemical concepts. Effective communication between teachers and students is achieved when teachers are able to use the correct chemical language that students can understand. In this section, you are going to learn how you can teach your students basic concepts in chemistry using the appropriate chemical language. In text question 2.3.1. Teaching chemical symbols, formulas, and equations. You would need many words to describe a chemical change using ordinary language, but you can do this with only a few letters and numbers in the language of chemistry. J.J. Bareilles laid the foundation of this language in the early 19th century. It gradually developed into its present form. In this language, an atom is represented by a symbol, a molecule by a formula, and a chemical change, i.e. a reaction by a chemical equation. In chemistry teaching, these concepts should be taught with the use of appropriate chemical language. In text question, one of the major problems associated with the use of symbols and formulas is misunderstanding the meanings associated with them. The historical development of modern chemical symbols started with Dalton's atomic model and Berzelius' proposals to use letters. Other known chemists had been using these ideas since then, and during the 19th century the logical way of scientific discussions in chemistry was in the following sequence: Bark and Temeggen, 2001. 1. Phenomena, properties of substances, masses, and volumes. 2. Empirical and molecular formulas. 3. Structural imaginations and structural formulas. It has, however, been argued that chemistry should be introduced to beginners with the help of structural models. Bark, 1997. Bark and Temeggen, 2001. This approach to the teaching of chemical symbols, formulas, and equations is described as follows. First of all, a number of significant phenomena should be demonstrated and discussed without using any particle models of matter or chemical symbols. As soon as the particle model is introduced, it should be applied to explain the different states of matter, dissolving processes, and chemical reactions. Only the structures of what substances looked like at the starting point should be illustrated, as well as the structure of the substances which appeared after they have gone through all the processes. For students to appreciate the significance of metals, salts, and other solids, and their descriptions through formulas and equations, students should first of all be introduced to the structures of these substances, such as sphere packing and crystal lattices as models of giant structures, ions as small particles of salts, and salt solutions. After students have learned about the structures of many solids, formulas are introduced to them by using structural models. The proportions of atoms or ions can be derived from sphere packing, lattices, or from unit cells. Bark, 1997, developed the overall system using the following figures sequentially as phenomena: structural imagination, chemical symbols. The three major categories in this approach to the teaching of chemical symbols, formulas, and equations are described as follows. Bark and Temeggen, 2001, 229. 1. Phenomena. Investigating phenomena in nature, or in the laboratory, showing substances and their properties, conducting experiments to show chemical reactions, offering students their own experiences by doing laboratory exercises. 2. Structural imagination. Taking structural models to show the structure of the substances involved before and after reactions, offering students the opportunity to build their own experiences by building structural models, developing structural images, and by handling these models. 3. Chemical symbols. Deriving formulas from demonstrated or self-built models, in order to give students the idea that formulas are shorthand forms of structural models, or of building units of the structure of molecules or unit cells. It is thus believed that such an approach lays the foundation for future use that is in accord with the 21st century thinking in chemistry. The approach also seems to be free from ambiguity, since it trains the students to see what kind of information is communicated by the symbols and structural models. The advantages of this approach are: Bark, 1997. Students will understand a chemical formula as a very short piece of information about the structure of the described substance. Along with structural models, students will accept the meaning of a formula and will never memorize it only as an abbreviation of the name. Students will have the opportunity to develop imaginations with regard to formulas and equations. Activity 2.4. In teaching chemical symbols, formulas, and equations at secondary school level, it is believed that at least the following points need to be clarified in terms of the real substances. Formulas mean different things for covalent and ionic compounds. Covalent compounds take, for instance, CCl. For this formula means not only that there are 4 chlorine atoms for each carbon, but also that these atoms are held together by covalent bonds in a definite order. This particle is called a molecule. In a small flask of the liquid, there would be billions of such molecules. But each molecule is a separate particle of CCl, for although its atoms are bonded to each other, they are not bonded to the atoms of any other molecule. In any sample of carbon tetrachloride, there will always be 4 times as many chlorines as carbons. Ionic compounds take, for example, NaCl in terms of the relative composition. This formula has the same meaning as does the formula for a covalent compound. In one small crystal of salt, or in a whole bottle, there will always be equal numbers of sodium ions and chloride ions. However, the situation in an ionic compound is quite different from that in a covalent compound, when one considers the individual particles found in the compound. Ionic compounds don't have molecules, the individual particles present are ions. In a Cl crystal, one cannot pick out one certain pair of Na plus and Cl ions and call it a molecule. Instead, each Na plus ion is surrounded by 6 Cl ions and is equally attracted to all of them, and vice versa. This situation, in fact, can be made clear only with the help of structural models such as sphere packing and lattice models. Teaching chemical symbols. Symbol is an abbreviation of the name of an element. When you explain the meaning of symbol, you ask one of the students to write his or her name on the board, and ask to spell out the name. You explain that just as we have alphabets in English language which we use to name different objects, we have symbols to represent elements in chemical language. You make the students aware that as there are many things we name around us, there are more than 100 elements known which combine in different ways to produce compounds that make up all the living and non-living things that we encounter. The historical development leading to the symbols of elements, and how these symbols were derived should be shared with the students in order to help them appreciate the development of representing elements using symbols. The list of the symbols and the names of few elements can be referred from students' text, and pointed out that the Latin names of elements have some history related to them. The names of few elements were related to the region or place, for example, a francium, France; B. germanium, Germany; C. americium, America; D. europium, Europe. The names of few elements were related to the names of the scientists' people. For example, A. barium, Niels Bohr; B. curium, Marie Curie; C. einsteinium, Albert Einstein; D. nobelium, Alfred Nobel; E. mendelevium, Dmitry Mendeleev. Point out to your students 1 or 2 letters from the English or Latin names of the elements are used as a symbol to represent the element, and the first letter is written in capital and the second in small. Then show them how these symbols of elements have been derived in the following 3 different ways. 1. The first letter in capital of the English names of an element is used to derive the symbol of the element. Examples: to the first letter in capital along with one more letter in small of the English name of an element. This becomes necessary when the names of 2 or more elements begin with the same letter. Examples: in your conclusion, make your students understand what the symbol of an element actually represents. The symbol of an element represents that element in particular. For example, do you know that the symbol of sodium is Na, and that of chlorine is Cl? So, instead of saying the compound common salt is made up of the elements sodium and chlorine, the students say that it is made up of Na and Cl. They can also say that Ca is red-brown whereas O is yellow, and that Ca is a metal whereas Cl is a non-metal. B. The symbol of an element represents one atom of an element. In formula and equation, a symbol represents one atom of an element. More than one atom is a molecule is shown by a numeral coefficient and subscript. For example, the formula for sodium chloride, NaCl, shows there is an atom of sodium and one atom of chlorine. In the formula of water, H2O, there are 2 atoms of hydrogen and 1 atom of oxygen. Assignment 2.2 B. Teaching chemical formula. In most cases, a chemical formula is defined as a symbolic representation of the composition, and, in some cases, the structure of a molecule of a compound. Such a definition presupposes that all chemical compounds exist, or have molecules. But the development of solid-state science in the 20th century has brought to our attention that symbols and formulas represent different things in the 3 states of matter. In the case of gases, one can certainly talk about molecules of a compound. However, in the solid and liquid states, the situation is more complex than it is represented by the traditional chemical symbols and formulas. Formulas are one of the chemical languages we use to show the composition, and in some cases the structure of a molecule of a compound. A molecule is the smallest part of an element, or a compound, that can exist independently. It is represented by a formula. The formula of a molecule gives the number S of atoms of the same or different elements present in the molecule. Several problems arise in the use of symbols and formulas. The major problem is memorizing the so-called molecular formulas without understanding the real particles composing the compound. Students usually have certain formulas in mind, without the correct imagination of what is behind them. Bark, 1997. Consider the formulas used by most chemistry curricula for calcium chloride and sodium hydroxide CaCl2 and NaO. According to Bark, when students are asked about the structure of these solids or particles in their solutions, they very often answer Cl CaCl or NaOH. Such observations imply that the students tried, in such cases, to apply the structure concept of covalent bonding in molecules, or the valence concept to substances, like salts or salt solutions. Although Arrhenius has clearly illustrated the concept of ions through his investigation of salt solutions, and although von Lau has shown the infinite nature of salt crystals, it is disappointing that the concept of molecules of salt still exists in the language of chemists. In-text question. Another problem comes from the use of symbols for solid elements. After reading in most chemistry textbooks such facts as a C stands for one atom of carbon, and B a formula shows what kind of atoms and how many of each are present in a molecule. Because of this kind of definition, and because we write she, ka, fe, na, etc., there is a strong belief that solid elements are just collections of atoms. However, the development of chemistry, particularly solid-state chemistry, has shown that it requires over 50% more energy to dissociate 2 by 63.5 G of copper in 2 separate atoms than it does to dissociate 2 by 1 G hydrogen in 2 separate atoms, although there is the same number of atoms in both cases. Students did not realize, under such circumstances, that atoms in elements are in many cases even more strongly bound together than they are in many compounds. A fourth difficulty comes from the existence of non-stoichiometric compounds, which cannot be represented by traditional types of chemical formulas. As students advance in their study of chemistry, they encounter such compounds as solid solutions, alloys, which are basically crystalline phases that can have variable compositions. Simple solid solutions could be of 2 types. West, 1984. Another difficulty arises from the use of the same symbols with different meanings. An example is the different meanings attached to the symbol C. See the element carbon. 1 atom of the element carbon. The mass of 1 atom of the element carbon. 1 mole of carbon atoms. The mass in G of 1 mole of carbon atoms. In addition to such different meanings, a symbol of a gaseous element such as He, Ne, etc., is used to represent the volume occupied by 1 mole of the element. Such ambiguity would have a considerable impact on the proper understanding of chemistry, particularly at school chemistry level. In teaching chemical formula, in order to overcome the problems observed, students should have the correct imagination of what is behind the molecular formula representation by understanding the particles composing the compound. You teach concept of atoms, molecules, and ions before discussing about chemical formulas. You introduce this topic with the help of a chocolate bar or any similar outline. Try to break the last chocolate cube into smaller cubes until the last chocolate cube is obtained. If we try to break the cube further, it may no longer be a cube. At this point, bring to the attention of students that just as the small cube is the building block of the chocolate, an atom is the building block of a molecule. Atoms usually don't exist independently with the exception of a few elements, like noble gases. The atoms of elements generally combine easily among themselves to form molecules. A formula of a molecule shows what kinds of atoms, and how many each, join together when a molecule is formed. A number, after a simple S subscript, shows the number. It means that there is 1 atom of the element. Give examples of formula of elements such as 2 atoms of hydrogen H combined to form a molecule of hydrogen. The formula is H2. Similarly, show to your students that of nitrogen, oxygen, fluorine, chlorine, bromine, and iodine contain 2 atoms of the element, and are represented as N2, O2, F2, Cl2, Br2, and I2 respectively. When atoms of two or more elements combine, a molecule of a compound is formed. These elements have different combining capacities, and the capacities of these elements to combine with each other determine the formula of the compound formed. Therefore, introduce about valency to your students at this point. Capacity of an element to combine with other elements is known as its valency. Show with the following examples that the combining capacities or valency of all elements are not the same. 1. One atom of Cl combines with one atom of H to form one molecule of hydrogen chloride HCl. Both Cl and H have valency of 1. 2. One atom of O combines with two atoms of H to form one molecule of water H2O. Here, the valency of oxygen is 2. 3. One atom of N combines with three atoms of H to form one molecule of ammonia NH3. Here, the valency of nitrogen is 3. 4. One atom of C combines with four atoms of H to form one molecule of methane CH4. The valency of carbon is 4. Thus, the combining capacity of O is twice that of Cl, that of N is thrice of that of Cl, and combing capacity of C is 4 times that of Cl. You can further show such differences in valencies of elements by taking other examples. The concept of formula writing can be introduced after students know about valency of atoms and the type of compounds. Show students how the formula of a binary compound, i.e. a compound formed by two elements only, is obtained. When compounds are formed from their respective elements, the total combing capacity of the first element should be equal to that of the second element. This is obtained by transposing their valences. Make your students write the valency of each element as a superscript to its symbol and transpose crisscross their valency, and write the corresponding formula as a subscript to get a formula for the compound. Suppose an element A has a valency Y and element B has a valency X, then the compound formed between A and B usually has the formula X by. It is important to also for students to know that the subscripts should be divided by a common factor, if any, to get the lowest ratio, which gives the final formula of the compound. There are some exceptions, like H2O2 hydrogen peroxide, Na2O2 sodium peroxide, etc., in which the numeral subscripts are not divided by the common factor. Give more examples that can help students understand writing the formulas of different compounds. Give exercise to students where they requires to find out the valencies of elements from the formula of a given compound. This will increase their understanding of a formula. Activity 2.5. C. Teaching chemical equations. Students know that an element is represented by a symbol and a compound by a formula. They also know that chemical change takes place when compounds combine, leading to different products, which is known as chemical reaction. Make your students to recall the characteristics of chemical reactions, such as evolution of a gas, formation of a precipitate, change of color, change of temperature, etc., which indicate whether the reaction has taken place or not. The actual reaction can be represented in short in terms of symbols and formulas called chemical equation, which are the shorthand notation of the chemical change. The terms reactants and products can be explained to the students, can be taught to write the word equation for the reaction. The words may be replaces with symbols and formula to get the chemical equation. Demonstrate or explain in observations of some reactions, and encourage your students to write the word equation using the names of elements or compounds, and the skeleton equations using symbols and formulas. Some suggested examples are: 1. Burning of magnesium ribbon and oxygen produce white light, which forms magnesium oxide as a white residue. 2. When granules of ZN metal added to hydrochloric acid HCl, bubbles of a gas are seen around granules, which are tested using burning splinter to be hydrogen gas H2. The surface of the metal becomes dull, which is due to the formation of magnesium chloride. 3. The color of copper sulfate solution is blue. After reaction with iron nails, the color slowly changes to liquid green due to the formation of iron sulfate, and reddish-brown deposits of copper metal are seen at the bottom of the test tube. Chemical equations written by students should be checked and mistakes done by students corrected by giving proper feedback. Once the students have learned to write equations, introduce the law of conservation of mass. The law stated that matter can neither be created nor destroyed in a chemical reaction. This means that the total mass of all reactants must be equal to the total mass of the product. The number of atoms of each element on the reactant side must be the same as that on the product side, that is, no atoms are lost or gained in a chemical reaction. When this is done, the equation is said to be balanced. The steps of balancing equation by trial and error method may be explained to students. Give students more exercises on writing balanced chemical equations. This topic can be grasped properly by the students only if they try to attempt different types of equations. Unit Summary. Language is closely related to concept learning. It is used to express meaning of concepts. When teaching chemistry, we use formal and chemical language to communicate knowledge to our students. There are different ways in which students learn language. Therefore, it is important to know how students learn and use chemical language, the rules which govern its use, and what is its effect when used for teaching chemistry. Chemical language is used to express the composition, structure, properties, and reactions of substances. It consists of a set of symbols to represent elements, formulas to represent compounds using elements, rules for writing equations, and use of specific names, common and systematic names to identify compounds. The knowledge of how to teach chemical language is necessary for teaching chemistry. Teachers should know how to teach chemical symbols, formulas, and equations. They have to use appropriate methods to teach each term in order to make their students understand the correct use of chemical language to communicate chemical ideas. Words and other symbols used to explain concepts should be related to experiences of the students. In order to overcome problems of teaching chemical language, students should have the correct imagination of what is behind to the chemical language used to represent the concept and the events. They have to understand familiar words used to express meaning in chemistry and the context under which they are used. Technical terms should be explained correctly to convey different quantities and phenomena. The use of everyday meaning to explain chemical events needs special attention in teaching chemical language. The use of different suggestions for teaching chemical language presented in this unit will be important inputs for teaching chemical language. Unit delivery approaches, methods, strategies, role play, class observation, interview, independent work, presentation, questioning, reflections, class exercise, problem solving, group discussion, problem solving, concept mapping. Learner's activity. Summarize language-related problems in the text. Actively participate in presentations and class discussions. Work on individual and group assignments. Check language-related problems in Teacher's Guide. Prepare reports and discuss in a class. Identify mathematical language-related problems from the textbooks. Poster work. Instructors' activities. Introducing contents and teaching methods. Facilitate during class discussion. Assisting learners in identifying language-related problems. Commenting on students' work. Check students' report on language-related problems. Evaluate students' presentations. Assessment strategies and techniques. Evaluation of reports on language-related problems. Evaluating students' presentations. Observation during group discussion. Giving surprise tests. Evaluation of peer teaching.